Hey Calkies, welcome to another lecture. This lecture is about concavity, and concavity deals with the shape of the graph, the curvature of the graph. The graph of a function f of x is concave up if, when we imagine it to be a cup, it holds water. Now, a graph usually is either concave up or concave down. The graph of a function is concave down if, when we imagine it to be a cup, it does not hold water. So remember that. Concave up, it holds water. Concave down doesn't hold water. And now that I've given the definitions, let me clear some more board space so I can put some better pictures up here. The ones I have are fine. I just need more than what I got already. So let's look at some more. Y equals f of x. And let's see, what would I like to do with this one? Yeah, that looks good. And y equals f of x. Okay. This graph, because of the way it curves, there's a little bit of water down here that it's holding. So we're going to say that this graph holds water, and it's going to be concave up. This graph here, look at it. The water can't cling to the surface because of the curvature. These are the drops of water falling out. This one's definitely concave down. And same thing for this one. Look at the curvature of the graph. There's no place for the water to collect here. The drops of water are just falling down. So this guy's concave down also. And over here, yeah, because of the curvature of this graph, the water collects right here at the bottom. So this graph definitely holds water, and it is concave up. This graph, well, we know what's going to happen. The water's not going to collect here. The water's going to fall right off the top. Look at these raindrops just falling off. This graph doesn't hold water. It's going to be concave down. And then finally, this guy over here, because of the curvature, the water gets a chance to collect right around there. So we say concave up. So we have an idea what a function that's concave up or concave down looks like. Now sometimes the graph of a function can switch. It can be concave up some places, concave down other places. Let's take a look at a graph that has that characteristic. Here's a nice example, just something that we can do by inspection. List the intervals on the x-axis over which the graph of f of x is either concave up or concave down. So we're going to write down the intervals on which f of x is concave up, and we're going to write the intervals over which the graph of f of x is concave down. And just to give us a little bit of room here, let me erase this junk at the top. F of x is concave up. On the intervals, and we'll list those, and concave down on the intervals. Well, I'd write the words, but I'm out of space. Now, judging from the way this graph looks, I can see the graph's concave down here. It doesn't hold water. And apparently, this is the way the graph continues this way. The graph goes down to negative infinity, and it continues to be concave down as we go to the left. So here the graph is concave down. What happens at this point? We have a relative maximum, but here the graph is concave down, here the graph is concave down. Concavity doesn't change here. Now right here, the graph changes from concave down to concave up. So I think the graph is concave down on the x-axis from negative infinity to this point, C2. So for concave down, I'm going to put negative infinity, negative infinity, C2. Now let's see. Here the graph is concave up. What happens here? Right here we have a relative minimum. It's a low point on the graph. But to my way of thinking, the graph is concave up here, and it's concave up here. It's going to hold water on both sides of this point. So I don't see the graph changing concavity from here to here. I think that from this point to this point, the graph is concave up. So from C2 to C4, I think the graph is concave up. C2, C4. Now, if we keep on going, the graph's concave down here, and at this point we have a relative maximum, and as we go from left to right past the relative maximum, it still looks like the graph is concave down here, doesn't it? It's not holding water. So I'm thinking concave down here, concave down here. The concavity doesn't change at this point. And I think the graph is concave down until we get to right about this point, and then the shape starts changing to concave up. So I think from this point to this point, the graph is concave down from C4 to C6. And then from C6, the graph is concave up. Here we have a relative minimum, but the concavity doesn't change here. The graph holds water here, the graph holds water here. Concavity doesn't change. So I'm thinking concave up from here to here, from C6 to C8, concave up. And at C8, something weird happens. Doesn't happen very often, but I guess it does happen. We have a relative maximum here. We do. It's one of these funny type B critical number relative maximums. And anytime we see a relative maximum that comes, or a relative minimum that comes to a sharp point, it's a type B relative maximum or minimum. These smooth, round relative maximums and these smooth, round relative minimums, those are type A critical number relative minimums and relative maximums. When we have a jagged edge relative maximum, that's a type B critical number. And we have a relative maximum here, and son of a gun, the graph also changes concavity here. The graph is concave up here, and it's concave down here. So the graph changes from concave up to concave down at C8, and from x equals C8 to x equal infinity, that graph is concave down. Now, not all of these points that I've labeled here on the graph are such that the graph changes concavity. Some of these points are critical numbers where we have a relative max or a relative min. Others, they're not a relative max or a relative min, but the graph changes concavity there and there. So we have a name for a point like that. And as soon as I can clear out some space to write, I'll tell you what the name is. Okay, I've just defined point of inflection. A point CF of C on the graph of f of x, like this one, is a point of inflection exactly when f of x changes concavity at that point. So this would be a good example. This is a point on the graph of f of x, and right here, the graph changes from concave down to concave up. So C2, f of C2 is a point of inflection. And I'm going to clear out some more space here and maybe move that label. Points of inflection. Here's one. C2f of C2. The graph changes from concave down to concave up at that number. So this is a point of inflection. Now the graph is concave up here and concave up here. There's no concavity change here. But what about this point? Here the graph is concave up, and then all of a sudden it's concave down. So this is a point of inflection. C4, f of C4. I wonder if we have any others. Let's see. Concave down here, concave down here. Nope, no change of concavity. Concave down here, concave up here. The graph changes concavity here, so C6, f of C6 is a point of inflection. The graph changes from concave down to concave up at this point. Let's see, this point, concave up here, no change in concavity. Now, what about this point? Concave up here, concave down there, point of inflection. Well, this is a very interesting point. It doesn't happen very often. At this point, we have a relative maximum. It's also a point of inflection where the graph changes concavity. Now, we have a conceptual idea of concavity. And we've identified or given a name to a point on the graph where the function changes concavity. If we don't know what the function looks like, how are we going to know where the function is concave up and where it's concave down? We'll talk about that in just a minute. Okay. The second derivative in concavity. Here's why we were interested in the second derivative. It turns out that if the second derivative is positive, then the original function f of x is concave up. If the second derivative is negative, then the original function f of x is concave down. And notice the natural association. Positive, concave up. Negative, concave down. It's natural to associate positive with up, negative with down. And think about this too. Our interest in the first derivative, f prime of x, and the second derivative, f double prime of x, rests in the fact that each one of these things tells us something about the original function. We're not as caring as we'd like to give ourselves credit for. We don't really care about the first derivative because we like it. We just care about it because of what it tells us about the original function. And we really don't care about the second derivative because we like it. We only care about the second derivative because of what it tells us about the original function. The first derivative tells us increasing and decreasing. The second derivative tells us concave up and concave down. That's why we're interested in the first derivative and in the second derivative, because of what it tells us about the original function. And the first derivative and the second derivative each tell us something different about the original function. Now remember, we said what a point of inflection was. A point CF of C on the graph of f of x is a point of inflection exactly when f of x changes concavity at that point. It either changes from concave up to concave down, or it changes from concave down to concave up. Now let's take the first case. Suppose f of x changes from concave up to concave down. What's the second derivative going to be doing? If the original function changes from concave up to concave down, then the second derivative changes sign from positive to negative. And if the original function changes from concave down to concave up, then the second derivative changes from negative to positive. So we can restate this point in terms of the second derivative. The point CF of C is a point of inflection exactly when the second derivative changes sign at the point CF of C. So if we have a point of inflection at CF of C, the second derivative has to change sign right here. And you know what? There's only two ways that that can happen. And this is very analogous to critical numbers in the first derivative. See, in order to have a point of inflection, the second derivative has to change sign at x equals c. One way that that can happen is if the second derivative evaluated at c is 0. And you'll never guess what we call x equals c. Well, maybe you might. X equals c is a type B point of inflection. No, I'm not. Excuse me, it's getting late. Type A point of inflection. Second derivative 0, type A point of inflection. Now, it is possible that the second derivative is undefined. And in this case, x equals c is a type B point of inflection. So the second derivative tells us about concavity and points of inflection where the concavity changes. What do you think? Are you ready for an example? I think we are. This is a goodie. This is a goodie. Determine the intervals over which the function is concave up and concave down. Identify all the points of inflection. So where should we start? We're interested in concavity, right? And what tells us about concavity? The second derivative. So we go straight to the second derivative. And we also find possible points of inflection. F prime of x is 4x cubed minus 6x squared minus 24x plus 3. And f double prime is 12x squared minus 12x minus 24. And we're going to look for points of inflection. And the identifying characteristic of a type A point of inflection is that the second derivative is 0. So we set the second derivative equal to 0, and we solve for x. You know what? These numbers are pretty big. And I've noticed that every term has a factor of 12. So I'm going to divide both sides by 12. Okay, now I can factor this. This monster, I don't know if I could have factored that or not. And I think I have x plus 1, x minus 2. Am I right? Let's see. Plus x minus 2x is negative x. Yes. X equals negative 1. X equals 2. And I'm going to say that these are candidates for points of inflection. Now, why don't I just say that they're points of inflection? And here's the reason. Our definition of points of inflection is not the perfect analog of the definition of critical number. With the first derivative and critical number, if the first derivative is 0, then that value of x is a critical number. But because of the way that we define point of inflection, we can't just say that a value of x is a point of inflection because it makes the second derivative 0. Because our definition of a point of inflection is that it has to be a place on the graph where f of x changes concavity. Now, these are going to turn out to be the only two places on the graph where f of x can change concavity. But we have to verify that the function changes concavity here for x equal negative 1 to be a point of inflection. And we have to verify that the graph of f of x changes concavity here to verify that x equal 2 is a point of inflection. And before I run my mouth so much that I forget that I haven't looked for type B points of inflection, I'll do that right now. And there are such things, type B points of inflection. That's where the second derivative is undefined. And typically that means we've divided by 0 in the second derivative. But look at our second derivative. 12 times x squared minus 12 times x minus 24. There's no division in the second derivative, so there's no way that we can be dividing by 0. So for our type B critical number, we give it the traditional ain't got none. No type B critical numbers here. So we've got our candidates for points of inflection. And now we need to know where the second derivative is positive and where the second derivative is negative, because that will tell us where the original function is concave up and where it's concave down. Now, how do you think it is we're going to find out where the second derivative is positive and where the second derivative is negative? How do we do that? How should we go about trying to find out where the second derivative is positive and where it's negative? Well, first thing I'm going to do is write down my second derivative up here for safekeeping. And my candidates for points of inflection, x equals -1 and +2. Okay. So have you figured out how it is that we're going to find out where the second derivative is positive and where it's negative? If you haven't, I'll tell you in just a minute. Did you figure it out? If we want to know where the second derivative is positive and where it's negative, we draw a sine graph of the second derivative, and we use the candidates for points of inflection to partition the x-axis. And then, from each interval, we choose a test value to plug into the second derivative. Wow, talk about deja vu, huh? Okay, well, here's our second derivative. F double prime of x equals 12x squared minus 12x minus 24. And our possible points of inflection are -1 and 2. And from each of these intervals, we'll pick a test value to plug into the second derivative. And this is my favorite right here. Whenever I can get 0 as a test value, I'll plug it in. So I plug 0 into the second derivative, I get -24. When x is 0, the second derivative is negative. And that means that the second derivative is negative throughout this whole interval. Oops, better give myself a little more room there. Second derivative less than 0. Okay. Now I'll pick a test point over here. 3 is a good test point. You know what? 10's a good one too. I'll plug 10 in for x. I get 1200 minus 120 is 1080. Minus 24 is 1046, I guess. Well, whether that's exactly right or not, I'm absolutely sure it's positive. When x is 10, the second derivative is positive. And that means the second derivative is positive throughout the whole interval from x equal 2 to x equal infinity. Now, over here, might as well do the same thing. Take -10 as a test value. Squared, we get 1200. Plus 120 is 1320. Minus 24 is 1296. Now, we don't care much about the 1296, but the positive part we care a lot about. When x is -10, the second derivative is positive. And that means it has to be positive throughout this whole interval because there aren't any other candidates for points of inflection at which the second derivative can change sign. So second derivative positive here, and second derivative is positive here. And you know, I think I pretty much have this whole thing whipped. I really do. Wherever the second derivative is positive, that means the original function is concave up. And the second derivative is positive on the interval from negative infinity to negative 1 on the x-axis. And also on the interval from 2 to positive infinity. And I'm going to remind myself of how I know this. It's because f double prime of x is positive on those intervals. F of x concave up, second derivative positive, and vice versa. Now, where is f of x concave down? F of x is concave down wherever the second derivative is negative. And this is the only place where it's negative, from x equal negative 1 to x equal positive 2. That's the only place. And we'll remind ourselves of why it is that f of x is concave down on that interval. It's because the derivative is negative. So we know where f of x is concave up. We know where f of x is concave down. And what about points of inflection? Those are points on the graph where f of x changes concavity, right? And f of x changes concavity from, at the point negative 1, it goes from concave up to concave down. And at x equal 2, it goes from concave down to concave up. So, negative 1, f of negative 1, and 2, f of 2 are points of inflection. Because f of x changes concavity at these points. So negative 1, f of negative 1, and I should give the y coordinate here. If I plug negative 1 in here to the original function, I get 1. Negative 1 cubed is negative 1 times negative 2 is plus 2. Negative 1 squared is 1 times negative 12 is negative 12. Negative 1 times 3 is negative 3 plus 6. So what do we have here? 1 plus 2 is 3 plus 6 is 9. Minus 3 is 6 minus 12 is negative 6. So negative 1, negative 6 is 1 point of inflection. And 2f of 2, I need to get the y coordinate for that point too. Let's see, 2 to the 4th is 16. 2 cubed is 8, times negative 2 is negative 16. 2 squared is 4, times negative 12 is negative 24. 2 times 3 is 6, plus 6. So 16 minus 16 is 0. Minus 24 is minus 24. Plus 6 is minus 18. Plus 6 is minus 12. So here are the points of inflection and the intervals on which f is concave up and concave down. Great example, right? I will set you free with a bunch of those from homework.